Hi, welcome to Advanced Math, Unit 12 on Vectors, Part C, page 3. So in the last section, last couple of pages, we looked at how to multiply vectors together using the dot product. And the first thing we're going to do on this page is try just doing it on a simple example in 2 dimensions. I've got a picture here of two vectors, u and v, and I want to compute their dot product, u dot v. And remember that our definition of the dot product is that you take the magnitudes of the two vectors, multiply them together, and multiply that by the cosine of the angle between them. So in order for us to do this, we need to figure out what the lengths of the vectors are, calculate magnitude of u, magnitude of v, and then get the angle and find the cosine. So finding the lengths of the vectors, the magnitudes, is going to involve a little Pythagoras. So to do that, let me pick a blue pen. I'm going to work in the margin down below the graph here. So the magnitude of vector u, let's say, is going to be equal to the square root of the sum of the squares of its components. And the x component is 2, so it's going to be 2 squared, and the y component is 7 squared. Well, that's going to be the square root of 53. And if I type that into my calculator, I'll get about 7.3 units as the length of vector u. So vector u, as I've drawn it on this grid, is about 7.3 units long. Now, vector v, let's take its magnitude using the same technique. Its horizontal component is 5, so it's going to be 5 squared plus the vertical component is the same as the other one, it's 7 squared. So we've got the square root of 74, 74. And my calculator says that the square root of 74 is about 8.6. So let me fill in my work up here. Magnitude of u is about 7.3. Magnitude of v is about 8.6. Now, I need to know the angle between the two vectors. And if you're doing this on a printed piece of paper, you can take a protractor and measure the angle between these two vectors. If you're doing this online, like I am, and you don't have a protractor, it's kind of awkward to do this. In that case, what you can do is go to the addendum at the end of part C, and then you'll find an enlarged version of this picture with a protractor overlaid on it. And you can look at the protractor and decide what you think the angle is. And I'll notice that this vector isn't really drawn quite right. It's a little bit off of its point, so the angle is not exactly right. But when I do this, I get an angle, um, I don't know, about 52 degrees. It's probably not exactly that, but you could try it on the addendum and see what you think. But I'm gonna work with 52 degrees anyway. So let's say I measure the angle theta is 52 degrees, and I need to know the cosine of theta. So the cosine of 52 degrees is about, let's see, I go to my calculator, 50 degrees, take the cosine, 0.616, about. So that means the dot product, I can write this whole product out, is going to be 7.3 times 8.6 times 0.616, 7.3, 8.6. Yes, I'm using my calculator on screen. 616 multiply. Um, Rounded, well, 38.7. I'll write it big. 38.7 is the dot product. And I calculated that dot product just using the measured angle and a calculated length for vector u and v. Alternatively, if you're doing this on graph paper that had a uniform or a known spacing on the grid, you could use a ruler and measure the vectors. So there's lots of different ways you can do this. All right. Now, That's nice if you got the vectors drawn out and you can actually literally measure the angle. But what if you really only had the vectors in component form and you didn't want to go to the trouble, or suppose it was really grossly inconvenient to graph the vectors on a piece of paper so you could measure their angle? Is there another way that you can do this? And actually the answer is yeah. So the bottom of this page is a piece of math that I'm not expecting you to memorize or regurgitate or show me later on. I'm trying to show here another way of calculating the dot product based on um, the angle difference for cosine. So what I've got here is a picture showing vector u and vector v, and each of them has its own angle when measured with respect to the x-axis, right? And so the angle between these two vectors would be the angle alpha minus beta. And so the dot product of u and v is again the magnitude of u times v times the cosine of, yeah, alpha minus beta. That would give you that angle between the two vectors. Well, cosine of alpha minus beta, we did that in the last unit. There's an expansion for that. That looks like this. Cosine of the angle difference, cosine cosine plus sine sine. Easy peasy. Okay, so remember, this is u times v, the magnitudes of u and v times this whole thing. So when I expand this using the angle difference formula, it's actually going to be u times v, or magnitudes, times the left part of this, plus u, magnitudes of u and v, times the right-hand part of it. And furthermore, I can rearrange this multiplication and rearrange this multiplication so that the u vector is associated with the cosine of alpha, which is the angle that goes with u. And the v vector magnitude is associated with the cosine of beta, which is its angle. And likewise over here as well. So, funny thing, the magnitude of a vector times the cosine of its angle is its x component. That's its x component. Vector v and its cosine is its x component of vector v. And magnitude of u times the sine of its angle, that's its y component. And vector v's magnitude times the sine of its angle, that's its y component. So remember, each of these vectors, the v vector has a y component and an x component. And if you wrote it in component form, these numbers, these lengths would be those components. So going back up here, you remember we defined vector u as having components a and b, and vector v as components c and d. So that means vector u's x component is really just a, and vector v's x component is really just c. Vector u's y component is really just b, and vector v's y component is really just d. So this really nasty expression can be written in terms of its components, the u and v components. It just becomes a times c. That's the x component of u times the x component of v plus b times d, which is the y component of u times the y component of v. So it's multiplying the x components of the two vectors together, multiplying the y components of the two vectors together, and adding those results. And that is the same thing as the dot product of u and v. So I didn't actually literally have to do the cosine of anything. I didn't have to measure any angles. I didn't have to measure any lengths. As long as I've got these two vectors in component form, it's actually really easy to calculate their dot product. That's so cool and very powerful. Next up, page 4.